Artificial intelligence is not all that intelligent. While today's AI can do some extraordinary things, the functionality underlying its accomplishments has very little to do with the way a human brain works to achieve the same tasks. A biological brain understands that physical objects exist in a 3D environment which is subject to various physical attributes. It interprets everything in the context of everything else it has previously learned. In stark contrast, AI, and specifically machine learning, analyzes massive data sets looking for patterns and correlations without understanding any of the data it is processing. A machine learning system requiring thousands of tagged data samples is fundamentally different from the mind of a child, which can learn from just a few experiences of untagged data. Even the recent neuromorphic chips rely on capabilities which are absent in biology. This is just the tip of the iceberg. The differences between machine learning and the biological brain run much deeper. So for today's AI to overcome its inherent limitations and evolve into its next phase, artificial general intelligence, we must examine the capabilities and limitations of biological neurons and how these relate to machine learning. Doing so will shed light on what ultimately will be needed to replicate the contextual understanding of the human brain, enabling AI to attain true intelligence and understanding.
Future AI. Technologies that think.
To understand why machine learning is not much like your brain, you need to know a little about how brains work and about their primary cellular component, the neuron. Neuron cells are complex electrochemical devices, and this brief description just scratches the surface. I will be as succinct as possible, but bear with me, then we'll get back to machine learning. The neuron has a cell body and a long axon, which in your brain has an average length of about 10 millimeters, which is huge for a biological cell. The axon connects via synapses to other neurons. Each neuron accumulates an internal charge, the membrane potential, which can change. If the internal charge reaches a threshold, then the neuron will fire. The neuron's internal charge can be modified through the addition of neurotransmitter ions, which can increase or reduce the internal charge, depending on the sign of the neurotransmitter ion. These neurotransmitters are contributed from incoming synapses when the connected neurons fire, in an amount we'll call the weight of each synapse. As the weight changes, the synapse contributes more or fewer ions to the target neuron's internal charge. When the neuron fires, it sends a neural spike down its axon and contributes neurotransmitters through each synapse to each connected neuron. After firing, the voltage returns to its resting state, and the neurotransmitters return to their initial locations to be reused. This is significantly different than the process used by the theoretical perceptron, which underlies most machine learning systems. I'll explore these differences in a subsequent video. Perceptrons are great for some calculations, while neurons excel at others. Neurons are slow, with a maximum firing rate of about 250 hertz. Not kilohertz, not megahertz, or gigahertz, but hertz. A maximum of about one spike every 4 milliseconds. In comparison, transistors are many millions of times faster. The neural spike is about 1 millisecond long, but during the 3 millisecond period after a spike, where everything is being reset, the neuron cannot fire again, and the incoming neural spikes are all ignored. This will prove significant when we consider one principal difference between the neuron and the perceptron. The time of arrival of signals at the perceptron does not matter, while the timing of spikes in the biological neuron is vitally important. The reason neurons are so slow is that they are not electronic, but electrochemical. They rely on transporting or reorienting ionic molecules, which is a process much slower than electronic signals. Neural spikes travel along axons from one neuron to the next at a leisurely 1 to 2 meters per second, slightly more than walking speed, when compared with electronic signals which travel at nearly the speed of light. Getting back to machine learning, if we imagine that it takes 10 neural pulses to establish a firing frequency, more on this in the next video, now it takes 40 milliseconds just to represent a value. A network with 10 layers takes nearly half a second for any signal to propagate from the first layer to the last. Taking into account additional layers for visual basics and boundary detection, the brain must be limited to fewer than 10 stages of processing. The neuron's slowness also makes the approach of learning through many presentations of thousands of training samples completely implausible. If a biological brain can process 1 image per second, the 60,000 images of the MNIST dataset for handwritten digits would require 1,000 minutes or 16 hours of dedicated concentration. How long would it take you to learn these simple symbols? 10 minutes? Obviously, something really different is going on here. In part 1, we examined how a neuron's slowness makes its approach to learning fundamentally different from the thousands of samples required by machine learning. Now we'll take a look at the fundamental algorithm of the perceptron and how it differs from any biological model. The perceptron underlies most machine learning algorithms and is fundamentally different from any model of a biological neuron. The perceptron has a value calculated as a function of the sum of incoming signals via synapses, each of which is the product of the synapse weight and the value of the perceptron from which it comes. In contrast, the biological neuron accumulates charge over time until a threshold is reached. The perceptron has no intrinsic memory. Its value will always be the same for a given set of inputs. The neuron, on the other hand, combines its inputs with the current state of its internal charge. So there is a modicum of memory, and the output may be different for any given set of inputs. While many say the perceptron's value is analogous to the spiking rate of the neuron, this analogy breaks down because the perceptron ignores the relative spike timing or phase of an incoming signal and considers only the frequency. As a result, the biological neuron can also respond differently based on the order of the spike arrival, while the perceptron cannot. To provide an illustration, here is the brain simulator with a few neurons. First, see how the neuron in, which is firing continuously, is connected to the neuron out with a synapse of 0.25. You can see that the out neuron accumulates the incoming charge until the threshold is reached, and then it fires. Now consider this neuron stimulated by 2 input synapses, weighted +1/2 and -1/2. If the inputs alternate, the neuron will never fire because each positive input is followed by a negative input, which zeroes out the accumulated charge. If the inputs fire more randomly, the neuron will fire whenever 2 positive spikes arrive with no intervening negative spike. The perceptron model doesn't support this function because it ignores the timing and phase of the incoming signals. In both cases, the perceptron would see the average input frequency is 0.5 because it's half the maximum rate. So the perceptron model will give the same output, 0, in either of these 2 cases because the summation of the weighted inputs will always be 0 regardless of the input timing. This means that the perceptron model cannot be reliably implemented in biological neurons and vice versa. This is such an essential difference between the neural network and the biological neuron that I will devote a separate video to exploring it in greater depth, along with other biological factors which make today's AI different from the brain's function at a very fundamental level. The biological neuron models allow for single spikes to have meaning, rather than having a spike train represent a value. As the overwhelming majority of the brain's neurons spike only rarely, it is likely that many neurons do have specific meanings. For example, since you understand what a ball is, it is likely that your brain contains a ball neuron, or perhaps many, which fire if you see a ball or hear the word. In a biological model, that neuron might fire only once when a ball is recognized. The perceptron model of firing rates doesn't allow this, however, because the firing rate of a single spike isn't defined. We've all seen diagrams of the orderly layers of a machine learning neural network, in which the neurons of each layer are fully connected to those in the next. In contrast, the brain appears to contain lots of disordered connections. Because it is so difficult to trace out individual connections within the brain, we don't yet know what the brain's layering structure actually is. It is obvious, though, that it is not the orderly layer-by-layer structure of machine learning. While we don't think much about how solidly perceptrons and machine learning algorithms rely on this orderly layered structure, three problems arise if we allow perceptrons to have synapses from any other in the network. First, a huge increase in the number of potential synapses. Second, the need for two-phase processing of perceptrons, or neurons. And third, backpropagation requires a constant gradient descent surface, which is not possible with potentially looping synaptic connections. In a neural network where each layer is fully connected to the next, the number of synapses increases with the square of the number of neurons in each layer. If any neuron can connect to any other, the number of possible synapses goes up with the square of the total number of neurons, a much larger number. Machine learning systems typically represent every possible synapse, and this is essential to the dramatic speedups possible with GPUs. This is necessary even though most synapses could have a zero weight and don't actually influence the operation of the network unless their weight is changed. The brain's neocortex has 16 billion neurons. With the potential for any neuron to connect to any other, this means there are 256 quintillion possible synapses. In memory, this would require 256 exabytes with only 1 byte per synapse. It's a ridiculously large number. In the brain, most of these synapses simply don't exist. The number of actual synapses is estimated at 10,000 per neuron, totaling only 160 trillion. This is a much smaller but still staggeringly large number, 160 terabytes. A huge proportion of these synapses have near zero weights. I call these synapses in waiting, which are there to store a memory by changing weight quickly should the need arise. While it's possible to structure the data so that only non-zero synapses are represented, the blistering performance improvements of today's GPUs is likely lost if we do that. Recall that the fundamental algorithm of the perceptron sums the input values from the previous layer. If we allow connections from subsequent layers, we need to differentiate between the perceptron values which have already been calculated from the previous layers and those which are yet to be calculated because they include input from subsequent layers. If the algorithm doesn't include this extension, then the perceptron values will be dependent on the order of the processing of the perceptrons. In a multi-thread implementation, this would mean that the calculated values are indeterminate. To correct this problem, the perceptron algorithm needs two phases with two internal values. There is an implementation of this two-phase algorithm in the open source Brain Simulator 2 in the file neuronbase.cpp. This is a C++ program. I suggest you check it out. The final problem of adapting a more random neuron synapse structure to machine learning is that the backpropagation algorithm can't adapt to it. The backpropagation's fundamental gradient descent relies on a stable error surface. As soon as we allow for looping connections, that surface is no longer constant over time, and the gradient descent concept breaks down. As an example, any perceptron with a synapse to itself will have a value dependent on its own previous value. The backpropagation algorithm has no way of knowing the specific value of a specific perceptron, and so it cannot appropriately adjust the surrounding synapses. Machine learning algorithms rely on their ability to represent numbers with a high degree of resolution and accuracy. This is difficult or impossible with biological neurons. Moreover, the more accuracy is needed, the slower the neuron-based system will run. Any biological brain implementing the numerical precision required by machine learning would be too slow to be useful. In a computer or in your brain, both transistors and neurons represent information digitally. Transistors by taking one of two defined voltage states, and neurons by emitting spikes. Given such components, there are a number of ways to encode numerical values. First, the frequency of spikes, or bits, in a single serial signal. Second, the timing of spikes in a single signal. Third, some encoding of parallel signals. And fourth, some more complex encoding scheme like binary integers or floating point or Unicode. While it is theoretically possible that streams of neural spikes could encode binary numbers or Unicode strings, it is impossibly unlikely. The first three methods, however, do appear in your nervous system, and all of them exist in computers. In the brain, numeric values could be represented by the number of neural spikes in a given time period. But remember that neurons are really slow, with a maximum frequency of about 250 Hz or 4 milliseconds per spike. If we want to represent the numbers 0 through 10, we could allocate a time period of 40 milliseconds. If 10 spikes occur in that time period, we could say that represented 10, and if no spikes occur, that could represent 0, etc. But there are some issues with this approach. Because you can't have fractional spikes in 40 milliseconds, you can never represent more than 11 distinct values. If you want to represent 100 different values, you'd have to wait 400 milliseconds, nearly half a second, to know what value you've represented. This is much too slow to be useful. In this method, rather than counting the number of spikes in a given time period, we'll examine the timing between adjacent spikes. Many peripheral nerves fire faster with greater stimulation. Some retinal nerves, for example, fire faster with brighter light. Since the fastest firing rate is every 4 milliseconds, we might let that represent 10. Firing every 5 milliseconds might represent 9, 6 represents 8, etc. Now we could represent the same 11 values in 14 milliseconds instead of 40. Neurons are actually very good at this type of differentiation, and neuron pairs can easily detect if a spike timing is at any specific given level. If you wanted to detect 10 different values, you need 20 neurons. You might ask, if 4 milliseconds represents one value, why not let 4.01 milliseconds represent another? That way you could get any desired level of precision. While this is theoretically possible, unfortunately it doesn't work because of that old bugaboo noise. The brain is an electrically noisy environment, and neural spikes might jitter as much as a millisecond. Let's look at the receiving end of such a signal. By adjusting the parameters of a neuron model, it is possible for an individual neuron to respond to any specific firing timing or greater. That means that to differentiate 10 different signal timings, you need 20 neurons. Pairs of neurons, however, can detect which of two incoming signals is firing faster than the other with considerable accuracy. That means that while this type of signal is very useful for relative values, such as detecting a boundary between two levels of brightness, it is difficult to use to detect absolute signal values. A further issue is that while individual brain neurons can detect this type of signal, there is no known way for them to generate such a signal. The only known way for a neuron to generate, for example, a 6 millisecond versus a 7 millisecond pulse gap is for it to receive such an input signal. This makes any brain computation on this type of signal prohibitively complex. Consider a cluster of neurons to represent a signal. The greater the number of firing neurons in the cluster, the higher the value will be. Interestingly, human touch sensitivity uses this mechanism. The harder you press on your fingertip, the greater the number of sensory nerves fire. This has the benefit of representing any number of values in a single 4 millisecond firing time. But the practical limitation is that it uses lots of neurons. The maximum number of values which can be represented by neuron firing is likely around 10, and machine learning algorithms require much more precision than this. Machine learning's underlying concept of gradient descent presumes a continuous gradient surface, and using only 10 unique numeric values makes the gradient descent surface choppy and discontinuous. Further, the more values you need to represent information in the brain, the slower it will run. Fundamental to all machine learning systems is the idea of the artificial neuron, the perceptron. Let's zoom in on the core function which sums the weighted signals from the various inputs. Admittedly, there are a few cases where this process appears to work in a biological neuron, but for the majority of cases it doesn't. Later in this video, I'll show you why a biological neuron using this model will always calculate that 6 plus 1 equals 6. It will calculate that 1 plus 1 equals 2 only some of the time. The biological neuron has a membrane potential, or voltage, which I'll call its charge. The neuron accumulates charge from its input synapses, and the various synapses have weights corresponding to the amount of charge they contribute. When the charge exceeds a threshold, the neuron will fire, sending a neural spike to all the neurons to which it is connected and resetting the internal charge. For convenience, we'll call the resting charge 0 and the threshold level 1. The primary distinction between the biological neuron and the perceptron is that the neuron only emits spikes, while the perceptron usually expects inputs to be real numbers. Most machine learning professionals simply say that the perceptron's real number represents the spiking rate of the neuron. In the previous video in this series, I showed why this reasoning leads to neurons which can only represent a small number of distinct values. But the primary issue is that after a neuron fires, it cannot fire again for about 4 milliseconds. The refractory period. During the refractory period, all incoming signals are ignored. Consider a simple example. Imagine that our neurons represent a value from 0 to 10 in a 40 millisecond period, represented by the number of neural spikes emitted in that period. We'll start with a neuron labeled timing, which spikes once every 40 milliseconds just for reference. To represent a value of 6 in a neuron, we'd have a neuron emitting 6 spikes in the period. Let's assign our signal with a value of 6 to a neuron labeled 6 in this brain simulator simulation and connect it to the neuron labeled out with a synapse weight of 1. So out will fire shortly after 6 fires. Now let's assign another labeled 1 and set it to a value of 1 so it will spike once in every time period, and we'll add a small degree of randomness. For the summation to be accurate, we'd like out to spike 7 times in the time period, but it doesn't work out that way. Looking just at the value of 6 during the 40 millisecond time segment, out will be in its refractory period for 24 milliseconds. So there is a 60% probability that our signal from 1 will arrive during a refractory period and be ignored. If our 1 spike happens to sneak in and cause out to fire, the following spike from 6 will arrive during out's refractory period and be ignored. Therefore, if spikes are evenly distributed, there is no possibility that 6 spikes plus 1 spike will ever equal anything but 6 spikes. If the spikes are randomly distributed, there is some possibility that a neuron might compute that 6 plus 1 equals 7, but the probability is remote and varies with the distribution of spikes. You can get a better summation with neurons if the signal values are small relative to the time period. That way there is less likelihood of a spike arriving during the refractory period. For example, 1 plus 1 equals 2 will be calculated properly 80% of the time using a 40 millisecond period, and 98% of the time in a 400 millisecond period. But 400 milliseconds is far too slow and too limited to be useful for machine learning. As far as we know, the weight of a synapse can only be changed by near concurrent firing of the two neurons it connects. This is completely at odds with the fundamental architecture of machine learning's backpropagation algorithm, as I'll explain in a moment. The only mechanism we're sure of to adjust a synapse weight is called Hebbian Learning, often whimsically expressed as neurons which fire together, wire together. But as in all things biological, it's not as simple as that. Studies in synaptic plasticity yield curves showing that to strengthen a synapse connecting a source neuron to a target neuron, the source needs to fire shortly before the target fires. To weaken the synapse, the target needs to fire shortly before the source fires. This makes overall sense in that if one neuron contributes to another's firing, the synapse connecting them should be strengthened, and vice versa. But the raw data shows a large amount of scatter, meaning that the ability to set a synapse value is very imprecise. You can also conclude that to make any substantial change in a synapse weight, it takes repetitive spiking. Even in a theoretical environment without the scatter, the greater precision you want in a synapse value, the longer it will take to set it. Further, imagine the neural circuitry needed to set some specific synapse value, arranging for precisely the correct number of spikes in the correct timing to the source and target neurons. This is assuming the weight started at 0, which is yet another issue because there is no known way for the neurons to determine the current weight of any synapse. Finally, a network containing this synapse would modify the synapse weight somewhat whenever it spiked, so such a system couldn't maintain the accurate values anyway. Taking these things together, the whole concept of storing specific values in specific synapses is completely implausible. Backing out to the level of the neural network, you might think of the backpropagation algorithm as a little man sitting on the sidelines of a neural network. He looks at the network output, compares it to the desired output, and then dictates new values for the synapses within the network. In a biological system, not only is there no little man, there is no mechanism to dictate the weights of any specific synapse. You might wish to increase the synapse weight between neurons A and B by firing the two neurons at precisely the right time, but there is no way to do that either. You can't just request to fire B directly after A to increase the synapse weight between them because there is no way to fire any specific neuron in the network. There is another way to look at the entire synapse process, which makes a great deal more sense. Consider a synapse to be a binary device with a value of 0 or 1. Now the specific intermediate weight of the synapse represents the importance of that synapse or the likelihood of forgetting the data bit it represents. If we think in terms of neurons firing in bursts of spikes, perhaps 5, then any weight over 0.2 represents a 1, and any weight below represents a 0. Such a system can learn in a single burst, and the synapse weight gets closer to 1 with each subsequent successful access. This makes it immune to small random changes. This is a more plausible scenario to explain how synaptic weights are used in an actual neuron network to represent data, but it is completely at odds with machine learning approaches. By connecting a source neuron to a target through a synapse weight of 0.5, the target neuron will fire at half the rate of the source. In fact, it will divide by 2 for any weight between 0.5 and 1, so the precise synapse weight is not critical. For a weight of 0.2, for example, it's a divide by 5 system. Interestingly, although neurons easily divide neural signals, they are not capable of increasing them. There is no combination of synapses which will take a neural signal spiking every 10 milliseconds and transform it into one spiking every 5 milliseconds. This is important for directional hearing. If a sound source is directly in front of you, or behind, the sound will arrive at your two ears simultaneously. If it is directly beside you, it will arrive at the nearer ear first by about half a millisecond. How can a 4 millisecond neuron detect a sub-millisecond difference? If a target neuron is connected to two sources, one through a synapse weight of 1 and the other through a synapse weight of -1, if the -1 arrives first, even by a small amount, the neuron won't fire. If the 1 arrives first, it will. Now, very small differences in axon length between the ear and the detector can create minute delays which can be used to detect the sound direction quite precisely. To detect various differences in signal arrival time, your brain need only have multiple neurons with slightly different axon lengths. With the leisurely 2 meter per second speed that signals travel down axons, a 1/4 millimeter addition in the axon length will introduce an extra half a millisecond delay. In general, optic neurons fire faster with brighter light. To detect a boundary between a lighter area and a darker area, neurons need to detect small differences in the spiking rate. With a circuit similar to the previous, a pair of neurons can be set to spike one if one side of a boundary is brighter, and vice versa. It turns out that your brain can detect boundaries with much greater precision than you can sense absolute brightness or color intensity. And this is a source of numerous optical illusions and difficulties in computer vision. Here's how neurons might detect absolute brightness. The neuron model can be made more biologically accurate if we add charge leakage. When a synapse imparts a charge to a target neuron, the charge doesn't stay there forever, but leaks away. This effect can be used in a number of ways, the first of which will be to detect interspike timings. If you have a source connected to a target with a weight of 0.9, it will take 2 incoming spikes to make the target fire, but only if the second spike arrives before the charge has leaked below 0.1. In this way, any neuron acts as a frequency sensor, firing when the source is spiking at or above a specific frequency. This is governed by the leak rate and the synapse weight. A cluster of neurons driven by a single signal can detect the frequency of an incoming signal with considerable precision, but it takes a separate neuron for each frequency level to be detected. To differentiate this from the previous example, a pair of neurons can detect the difference in firing rate regardless of what the rates actually are. But to determine the absolute firing rate requires a neuron for each rate to be detected. So to detect 100 different levels of gray would require 100 neurons at each pixel. This is why you can only detect about 7 gray levels, but you can detect the boundary between gray levels which would appear identical if they were not touching. A neuron can act as a single bit of short-term memory. In a simple model, consider a neuron connected to itself. If it starts spiking, it will spike indefinitely until some suppressive signal causes it to stop. If the neuron is spiking, this represents a 1, if not a 0. This way, a single neuron can act as a single bit of short-term memory. This is easy to understand, but uses a lot of energy for that continuously spiking neuron, because neurons need energy to spike, but almost none otherwise. A better model stores the bit as the accumulated charge as opposed to the firing state. By connecting a set neuron with a synapse weight of 0.9, the internal charge of the bit neuron will be increased, but not enough for the neuron to fire. Now a second input from a read neuron will cause the memory bit to fire, but only if it has been set. To round out the picture, a reset neuron connected with a weight of -1 will clear the memory bit regardless of the state. As an added feature, the read neuron can also fire the reset neuron, and the firing memory bit can cause the set neuron to fire again, which will restore the memory bit once more. This means that the memory can store the bit, either 1 or 0, without consuming any energy by spiking until the memory is needed. Every time the bit is read, it is cleared and restored. To make this a bit more realistic, we'll add leakage back into the mix. Now the memory bit must be read before the internal charge leaks away. The reset signal becomes less necessary because if you just wait a second or two, the memory will fade away on its own. As long as you keep reading the memory, though, it will persist. This memory is using a mechanism of charge storage very similar to dynamic RAM, which must be refreshed periodically before the memory content leaks away. Although machine learning can do many things which the human brain cannot, the brain performs continuous speech recognition, visual interpretation, and a host of other things simultaneously, all while using only about 12 watts of energy. For comparison, my laptop draws 65 watts, and my desktop machine draws over 200, and neither of them is capable of running the huge machine learning networks which are in use today. The human brain is proof positive that general intelligence can exist in a system which is small and dissipates only 12 watts of energy. While machine learning has taken off into the realm of the largest, most power-hungry computers in the world, let's look at how the brain achieves its remarkable efficiency. I attribute it to 3 factors. First, the brain is physical and chemical rather than electronic. Second, the neurons in the brain are really slow. And third, neurons only require significant energy when they emit spikes. While we can use electronic instruments to measure voltages within neurons, their fundamental operation is chemical. Ions are migrating from one side of a membrane to another, and ionic molecules are changing orientation. This is fundamentally different from a computer where electrons are moved about and the charge they represent travels at nearly the speed of light. Obviously, molecules in the brain don't require any external energy at all when they are just sitting there. And the amount of energy needed to get a sodium ion to move from one side of a membrane to another is minute. I mentioned in a previous video in this series that neurons spike at a maximum frequency of about 250 Hertz, and neural signals travel along axons at a leisurely 2 meters per second. If we slowed our CPUs down to a similar pace, they would also dissipate a lot less energy, but likely not as little as their biological counterparts. But the real difference is that neurons need substantial energy only when they fire. Further, they don't fire very often. By taking the total energy of the brain and dividing by the energy needed to fire a neuron, as calculated by its chemistry, we conclude that neocortex neurons fire on average only once every 2 seconds. It's obvious that the continuous processes like vision and hearing must be running more or less constantly, using more energy, so to get things to average out, neurons in vast portions of the brain seldom fire at all. A neuron which represents a specific memory, such as a person you know, for example, likely only fires when you think of that person. Further, for most neural circuitry to work, many neurons must fire in bursts of 5 or more spikes, further reducing the number of neurons which are active at any given time. The idea that neurons are only active when the information they represent is active is fundamentally at odds with machine learning. Consider neurons representing a gray level at a single pixel, as I showed in the last video. In machine learning, a single neuron fires continuously with its firing rate defining the light intensity. A more efficient and more likely alternative is that 7 different neurons each represent a distinct gray intensity. Only one of them will fire a brief burst whenever a new gray level is encountered. This requires more neurons, but a lot less energy. But there's a further way to think about it. A CPU uses some amount of energy when it's running at speed, that is, not idle or asleep, and it uses this amount of energy largely regardless of the data it is processing. In a CPU, adding 0 plus 0 requires essentially the same energy as adding 12,345 to 67,890. Neurons are different. A neuron representing 0 doesn't fire and dissipates essentially no energy. This distinction has been the genesis of the neuromorphic computer field. In the brain simulator, processing is only required for neurons which fire, and so a desktop CPU can handle up to 2.5 billion synapses per second. Neuromorphic chips capitalize on this effect to produce AI results with radically less power than conventional machine learning processes. While neuromorphic systems have moved in the direction of more brain-like architecture, they are typically still using the machine learning backpropagation algorithm, which is not neuromorphic at all. Before closing the conversation on the efficiency of the brain, I'd like to point out one similarity which leads me to believe that brain-level computing is not nearly as far off as most people think. Our neocortex is folded into our heads in the well-known brain shape, but actually the neuron cell bodies are in just a few layers on the surface. And if the surface were unfolded, it would loosely represent a disk about 12 inches in diameter. The neurons and synapses on the surface represent the gray matter, while the interior of the brain represents the massive axonal interconnections, the white matter. Right now, many integrated circuits are created on silicon wafers, which, by coincidence, are also about 12 inches in diameter. With today's transistor densities, one of these wafers might theoretically contain over 3 trillion transistors. Your neocortex conceivably contains 160 trillion synapses, but these occur in several layers at the brain surface. Today's transistors are substantially smaller than either neurons or synapses, and the process of fabricating multiple layers of components on the surface of a wafer is beginning to gather steam. But these transistors are perhaps 1 billion times faster than biological synapses, so today's wafer of transistors represents millions of times the computing power of the neocortex. While the very real problems of heat dissipation and interconnection are yet to be solved, the idea that an AGI must be in a massive supercomputer is only a first step. To build a computer with brain-level computational power in a desktop or mobile device is well within the foreseeable future. Overall, the inescapable conclusion is that machine learning is not very much like a brain. In fact, a neural network consisting of things called neurons, connected by things called synapses, is about the limit of the similarity. The signals are different, the time scale is different, and the algorithms of machine learning are impossible in biological neurons for a number of reasons. Neurons are so slow relative to a computer that the way they work is fundamentally different. Sure, there are lots of interconnected neurons and they run in a generally parallel process like the idea of artificial neural networks, but there are some obviously serial processes like vision and hearing, and the neuron's slowness puts pretty hard limits on the number of stages possible in processing. If you can see or hear something and react to it in a fraction of a second, the number of processing layers in the brain is limited by the speed with which each layer can do its processing. The slow speed of processing in your brain also means that the huge training sets common in machine learning are implausible in a biological setting. The orderly layer structure of artificial neural networks is necessary to their operation. If signals from downstream layers are allowed to loop back to earlier layers, the fundamental backpropagation algorithm breaks down because the network's gradient descent surface is no longer constant. Looping connections give a neural network a degree of internal memory, so it has the capability of producing different results from identical inputs based on its internal state. This is great for the idea of more human-like thought processes, but not so good for a feed-forward artificial neural network. The algorithm of the perceptron is different and incompatible with what we know about biological neurons. The most basic summation performed by perceptrons doesn't work for neurons except in certain instances. The neuron's refractory period, about 3 milliseconds after every spike is emitted, will make neurons miss incoming spikes, and this leads to erroneous summations. In episode 5, I showed that the summation of 6 plus 1 always yields 6. Not 7, as the summation would suggest. In fact, the only situations where summation is reliable is in networks which are too slow with values too limited to be useful. In general, the idea that the value of a perceptron represents the spiking frequency of a biological neuron simply doesn't work. Machine learning relies on reasonably precise neuron values and synapse weights, neither of which is plausible in a biological setting. I showed that the more precisely a neuron value needs to be represented, the slower each network layer must run. A reasonable estimate of the number of different values represented in a neuron would be about 10, not the floating point numbers typical of artificial neural networks. Setting precise synapse weights is even worse. While some theoretical approaches to setting synapse weights might be useful, the observed biological data shows that synapse weights have a high degree of randomness. So high that I am led to believe that synapses are essentially digital, representing a weight of 0 or 1, and any intermediate values only indicate the confidence that that digital value is correct and or how easily that particular data item might be retained or forgotten. In my mind, the biggest problem with the idea that machine learning is like your brain is that backpropagation needs to set specific synapses to specific weights. As far as we know, there is no biological mechanism by which this might be possible. Synapse weights do change in response to near concurrent spiking of the neurons they connect, but the infrastructure needed to set any specific synapse would require several neurons, obviating the value of storing information in synapse weights at all. Finally, the incredible low power needed by the human brain comes primarily from the fact that neurons in your brain don't spike very often, once every 2 seconds on average. With these low firing rates, there is no possibility that your brain is represented by the more or less continuous firing represented by artificial neural networks. Sure, the more recent neuromorphic field has made some progress in the right direction, but for the most part, it still relies on backpropagation and setting specific synapse weights, neither of which is plausible. Taken together, and in combination with other issues presented in this series, these things mean that machine learning isn't much like a brain. While machine learning has made some remarkable advances, at Future AI, we are pursuing development of a self-adaptive graph structure, a system which has been shown to be possible in neurons and could be representative of how artificial general intelligence will be implemented. We're implementing an artificial entity, Sally. She uses a remote sensory pod to learn about her environment, build an internal mental model, and learn new actions to achieve her goals. You can help the project by visiting our website and signing up to participate in the Sally beta test later this year. This concludes our Machine Learning is Not Like Your Brain series. With that in mind, what would you like to see next from this channel? Let us know in the comments below. And as always, thanks for watching.